Hello, this is Mr. Keppel, and this is PHYZR number 13, What is Temperature? One of the most important concepts in thermodynamics is temperature. So the purpose of this lesson is to understand what is temperature, to discuss the various ways of measuring temperature, and understand that there's a coldest possible temperature known as absolute zero. Before we discuss what is temperature, let's talk about what thermodynamics is. So as you can see in this picture, this is a firebox, and it's inside a locomotive. This is a very good example of thermodynamics. Now before we break this down, let's first talk about the word thermodynamics. The word thermodynamics comes from the Greek words thermos and dynamis. Thermos for heat and dynamis for power. So put this together, we have thermodynamics is heat power. Now that we understand the root words, we can sort of get a feel for what thermodynamics means. But the actual definition of thermodynamics is it's the study of energy conservation between heat and mechanical work. The basic idea is if we begin with thermal energy, we can transform it into mechanical energy, and then back again into thermal energy. So any of these exchanges of energy between thermal energy and mechanical energy could be classified as thermodynamics. We're studying heat and mechanical work and the energy conservation between these two forms of energy. So to recap, inside the firebox in the train, we're burning a fuel, be it wood, coal, gasoline, diesel, and as a result, the train moves forward. We have a transformation of energy from thermal energy into mechanical energy. This is thermodynamics. So as you can see, a very important concept in thermodynamics is the concept of temperature. But we have to ask ourselves, what exactly is temperature? Is it just how hot something is or how cold something is? What physical mechanism gives rise to temperature? So what exactly is temperature? I'm going to pause here for you to think about that. You've probably heard this before, that temperature is molecular motion. It's the movement of the molecules within the object that gives rise to its temperature. So for example, if we have a cold glacier versus a hot geyser, and we were actually to look at the molecules in the glacier are moving pretty slow, and they're packed together. It's very dense. It's because ice, a glacier is made of ice. Ice is a solid. So the molecules are still moving. They're just moving very slowly. There's not a lot of molecular motion here. However, if we were to look at the geyser, we notice that the molecules are more spread out. They're moving more quickly, and it's less dense. So the geyser has more molecular energy than the glacier. The molecules are moving more rapidly in the geyser than they are in the glacier. What we conclude from this is that in a cold body, the molecules move slowly, and in a hot body, the molecules move quickly. So this is the difference between hot and cold. The molecules in a hotter object move more quickly than those in a colder object. When you measure the temperature of an object, this is what you're measuring. You're measuring the amount of molecular motion. This means the molecules have kinetic energy. So temperature is actually related to the kinetic energy of the molecules in the object. In a glacier, the molecules have a low kinetic energy, and in the geyser, the molecules have a high kinetic energy. So we see that there's a connection between temperature and molecular kinetic energy. Temperature is abbreviated with a capital T, and the unit of temperature, the International System Unit, is the Kelvin. And here's the definition of temperature. It's the average kinetic energy due to the random motions of the particles in a body. Like we just said, in an object with a high temperature, the molecules will have more kinetic energy than an object with a low temperature. When we say average, it's simply because inside the object, molecules are moving at all different speeds. And so we're just going to take an average of all the kinetic energies of all the molecules in the body. Essentially what this means is that temperature is independent of the size of the object or the mass of the object. Temperature does not depend upon an object's mass. It only depends on the molecular kinetic energy. Compare this to internal energy, which is symbolized with a U. The unit of internal energy is a joule. So internal energy is the total kinetic energy of all the particles in a body. Or we can say it's the total amount of thermal energy contained within an object. Hence, internal energy. It's contained within the object. So notice how these two quantities differ. They both deal with molecular kinetic energy. However, temperature does not depend on the size of the object, whereas internal energy does. The larger the object, the larger the total amount of kinetic energy is going to be. So internal energy depends not just on the molecular kinetic energy of the molecules, but also the amount of molecules in the object, or in other words, the mass. Let's check your understanding of the difference between temperature and internal energy. First, we'll begin with temperature. Between the glacier and the geyser, which has a higher temperature? In order to answer this question, we need to look at the average molecular kinetic energy. In other words, we need to look at the speed of the molecules. Because the glacier, the molecules move slowly, we know the temperature is cold. In the geyser, the molecules move quickly, therefore the geyser is hot. But how about internal energy? Which object has the greater internal energy? The glacier or the geyser? In other words, which object contains more thermal energy? The glacier or the geyser? Let's take a moment to think about it. So which object contains more thermal energy? Well, that's the internal energy of the object. Remember we said internal energy depends not just on the average molecular kinetic energy, not just on the speed of the molecules, it also depends on the mass. And we know that the mass of the glacier is much larger than the mass of the geyser. The glacier is this massive object, many, many miles across, whereas a geyser is pretty small. We also know that the temperature of the glacier was low, which means the molecules have a smaller kinetic energy in the glacier than they do in the geyser, where the temperature is hotter. So suppose, for instance, that the glacier, each molecule has an average of 1 joule of kinetic energy, whereas in the geyser, each molecule has 2 joules of kinetic energy. So which has a greater thermal energy contained within it? Well, in order to find that, we need to add up the total kinetic energy of all the molecules in the object. For the glacier, we can count up all these 1 joules, add them all up, we get 35 joules. We do the same thing for the geyser, we add up all the kinetic energies, and we get 14 joules. Surprisingly enough, the colder object, the glacier, actually ends up having a greater thermal energy than the hot geyser. And it's not because of the difference in temperature, it's because of the mass. So thermal energy, it's confusing. It doesn't mean hotness. You don't say, oh, the one with more temperature has more thermal energy. That is not always the case, because we also have to look at the mass. So don't let that confuse you. Now that we know what temperature is, let's talk about measuring temperature. Temperature is measured with a thermometer. The idea is that the molecular motion of the molecules bouncing around will then collide with this liquid inside this tube, and the faster the molecules are moving, the higher the liquid will rise. And the colder the molecules are moving, the lower it will go. The idea is that if the molecules inside the liquid in the thermometer are moving faster than the molecules surrounding the thermometer in the environment, then the molecules in the liquid will transfer their energy to the slow-moving molecules outside, and that'll cause the liquid to drop down. One of the confusing things about temperature is the fact that there are different scales of temperature. So as you can see on this thermometer, if I was asking you what is the reading of this thermometer, you wouldn't know whether to say 100 degrees F or 38 degrees C. Well, the difference here is those are two different scales. We have Fahrenheit for degrees F and Celsius for degrees C. Well, why do we have two different scales? Well, the idea was that the first person to invent the thermometer was Gabriel Fahrenheit, and he had his own unique way of distinguishing between the different temperatures. So he actually decided to set 100 Fahrenheit as human body temperature. And then he went to his laboratory, and the coldest temperature he can find in his laboratory, he set that as 0 degrees Fahrenheit. And then Celsius based his scale on water. So he said that water boils at 100 Celsius and freezes at 0 Celsius. So there's two different scientists that had two different ways of defining temperature. And so that's the reason why we have these two different scales. Of these two scales that we find on your typical thermometer, which is the standard unit of temperature? If you remember back, we said it was neither. The standard unit of temperature is actually Kelvin. We'll talk about that in just a minute. But first I want to talk about these temperature scales of Fahrenheit and Celsius. So in the Fahrenheit scale, water freezes at 32 degrees Fahrenheit. That's the freezing point of water. And water boils at 212 degrees Fahrenheit. That's the boiling point of water. Now these are weird numbers. They're not nice at all. Well, that's because Fahrenheit wasn't based on water. Celsius was based on water. The Celsius scale, water freezes at a nice 0 and boils at 100. This is the reason why Celsius is sometimes called centigrade, since there are 100 degrees between freezing and boiling in the Celsius scale. So which scale do you like better? Do you like Fahrenheit with the wacky 32, 212? Or do you like Celsius, which is 0 and 100? Personally, the scale I prefer is Celsius because it's much simpler, much easier to remember. The reason why Celsius and Fahrenheit are not the standard unit of temperature is because there is a coldest possible temperature, and that temperature is not 0 Fahrenheit and it's not 0 Celsius. It's actually way below that. The coldest possible temperature is called absolute zero. It's negative 459 degrees Fahrenheit and negative 273 degrees Celsius. This is 273 degrees below the freezing point of water in Celsius. Alright, so let's say that we have an object with a high temperature and we're going to slowly cool it down. We're going to cool it, we're going to remove energy, continually cool it, lower the temperature, lower it and lower it and lower it. Eventually what we see happening is the molecules get slower and slower, they clump together, and then finally they stop moving. At this point, we've reached absolute zero. Absolute zero is the temperature at which all molecular motion stops. If we're removing energy from a particle, when we've finished removing all the energy, so all the thermal energy is gone, then we've hit absolute zero. This is the coldest possible temperature. You can't get any colder or slower than not moving at all. You can't get any colder than that. That's just the end of the road. So now that we've reached absolute zero, a few questions to think about. Looking at these molecules, what is their average kinetic energy? And what is the temperature of these molecules? Take a moment to think about it. Since the molecules are at rest at absolute zero, they have no kinetic energy. So the average kinetic energy of the molecules is 0. And the temperature is absolute zero. It's negative 459 degrees Fahrenheit and negative 273 degrees Celsius. So you see the problem with Celsius and Fahrenheit is that we have 0 average kinetic energy, but we don't have 0 temperature. So this is a complete flaw with these scales. Now that we know there's a coldest possible temperature, we need to make sure that a 0 temperature is actually referring to 0 kinetic energy of the molecules. The way we fix that is by using the Kelvin scale. So we say absolute zero is negative 459 Fahrenheit, negative 273 Celsius, but now we have a new scale which is based on absolute zero, which says absolute zero is 0 Kelvin. And so we use this scale because 0 molecular kinetic energy is actually 0 temperature at 0 Kelvin. So that's why it's called absolute zero. It's not a fake zero, like Celsius, 0 degrees Celsius. That's not 0 temperature. That's just freezing water. In 0 Kelvin, that is actually truly, absolutely 0 molecular kinetic energy. At the top, we have the boiling point of water. In the middle, we have the freezing point of water, and down at the bottom, we have absolute zero. Our goal here is to be able to memorize these temperatures. These temperatures will serve as markers for us in terms of relating to and understanding all the temperatures. If we can memorize these 9 temperatures, we'll be able to do conversions on our head and sort of think on our feet about when you see a temperature, you can tell which temperature is hotter than another, even if they're not given in the same temperature scale. Unfortunately, if you look at this picture, you'll notice that Fahrenheit sort of stands out as being odd. So we're just going to ignore Fahrenheit for now. What we notice here is between Celsius and Kelvin, they both have 100 degrees between freezing and boiling. There's 100 between freezing and boiling. In fact, if we take these temperatures and subtract them, we notice that we always get the same result. We get negative 273. This is going to be very useful to us. So we realize that the difference between Celsius and Kelvin is always 273. From this information, we create this formula. It says Celsius subtracted by Kelvin is negative 273. If we solve this for Celsius, we find that Celsius is Kelvin subtract 273. So if you know the temperature in Kelvin, you subtract 273 and bam, you got your Celsius temperature. So for example, we know Kelvin is based on absolute zero. So if Kelvin were 0, we would have 0 subtract 273, and then we would have a Celsius of negative 273 degrees. We can also solve this for Kelvin, and if we do that, we get Kelvin is Celsius plus 273. So if you know the temperature in Celsius, you simply add 273, and then you'll have the temperature in Kelvin. So for example, boiling water is 100 Celsius. If we take 100 Celsius, add 273, we have 373 Kelvin for the boiling point of water. So now that we understand how Celsius and Kelvin relate, we can actually fill in this table. We've got the 3 temperature scales, Celsius, Kelvin, Fahrenheit, and then we have the 3 temperatures, water boils, water freezes, and absolute zero. Now there are 3 boxes here that we should begin with. The first is Celsius, the 2 simple ones in Celsius. We have freezes at 0, boils at 100. Very simple, very easy to remember those. Remember, Celsius was based on water, so those are the ones we begin with. And Kelvin is based on absolute zero, so we put 0 for absolute zero. With Fahrenheit, there aren't any easy numbers, so we're going to just deal with that later on. Okay, next, we know the difference between Celsius and Kelvin is always 273. To go from Celsius into Kelvin, we need to add 273. So 100 plus 273 gives us 373. 0 plus 273 gives us 273. And to go from Kelvin back to Celsius, we need to subtract 273, so we get negative 273 degrees Celsius. So notice that all we really needed to remember was 0, 100, and 273. And then we can figure out the rest. Fahrenheit, though, you're just going to have to memorize them. There's no easy way here. So remember, water boils at 212, freezes at 32, and absolute zero is negative 459. You're going to need to memorize the values in this table. They're going to be all over tests and quizzes in this class. You're going to really need to memorize these. So take a moment right now to pause the video, write these down, make sure you memorize these temperatures. The reason is because later on when we talk about heat flow, you're going to need to be able to tell which object is hotter, because heat flows from hot to cold. So for example, if I tell you that one object is 100 Celsius and another object is 32 Fahrenheit, which object is hotter? The common mistake students make is they say, oh, well, the one with the higher number is hotter. That's not always the case. What we should be doing here is thinking to ourselves not which number is larger, but which temperature is hotter. So realize that 100 degrees Celsius is the boiling point of water, and 32 degrees Fahrenheit is the freezing point of water. Clearly, boiling is hotter than freezing. Let's look at another example. 100 degrees Celsius or 273 Kelvin, which temperature is hotter? Here's an example where picking the bigger number actually gets you the wrong answer. So 100 degrees Celsius, again, that's boiling. But 273 Kelvin, that's freezing. That's the freezing point of water. So notice that boiling is hotter than freezing. 100 Celsius is greater than 273 Kelvin. Don't let this confuse you. You need to look at what the temperature is, not what the numbers are. Here's another. Negative 273 degrees Celsius or 32 degrees Fahrenheit. Which temperature is hotter? In this case, we have absolute zero and the freezing point of water. Since absolute zero is the coldest possible temperature, everything is hotter than absolute zero. So 32 degrees Fahrenheit is hotter than negative 273 degrees Celsius. Try this one. The weird thing about temperature scales is that 0 in one scale is not the same as 0 in another. This is unlike any other units of measure that we have. So for example, 0 miles and 0 inches, that's the same distance. But 0 Celsius and 0 Kelvin are not the same temperature. Because 0 Celsius is a fake 0 and 0 Kelvin is absolutely 0. In fact, 0 Celsius is freezing water and 0 K is absolute 0. And of course, freezing is hotter than absolute zero because everything is hotter than absolute zero. Absolute zero is the coldest possible temperature. Here's one last one to try. In this case, what we want to do is actually convert the Celsius into Kelvin and then compare the two numbers in the same temperature scale. So 100 degrees Celsius is boiling. Water boils at 373 Kelvin, which means 400 Kelvin is above boiling. And therefore, 400 Kelvin is the hotter temperature. Well, that's it for this PHYZR. This has been Mr. Keppel. I hope you guys have a wonderful day, and I'll see you in class.